Somewhere in the data from the most powerful telescope ever built, there are a few hundred small red points of light. They are not stars. They are not galaxies. Not in any sense we had a word for. Every telescope before this one looked straight through them and saw nothing at all. And in the 4 years since they turned up, serious people have published at least 6 incompatible explanations for what they might be. 2 of those explanations within 7 days of each other, this month. That is the state of things at the very edge of what we can see, and it is not the strangest part, because when this telescope looked further into the universe than anything in history, it found something genuinely disturbing, and it is not any single object out there. By the end of tonight, you will know exactly what it is, and why the people who found it have spent 4 years quietly taking their own discoveries apart. Settle in. Subscribe if you haven't already and stick around, because the thing that survived all of that dismantling is stranger than the headlines ever were. Let's get into it. Part 1. The Grain of Sand. On the 11th of July 2022, a photograph was shown to the world in a room in Washington, and almost everybody who saw it made the same noise. It was a beautiful picture. That was the point of it. It was chosen to be beautiful because it was the first thing a new telescope had produced after 25 years of construction and $10 billion of public money. And somebody very sensibly decided that the first thing the public saw should be something that made them glad they had paid for it. There were points of light in every direction. Some of them white, some of them a warm amber, some of them a strange cold orange that no astronomical image had ever quite shown before. In the middle there was a cluster of fat, bright, fuzzy shapes, and around that cluster the light bent into thin, curved streaks, as though somebody had taken a photograph of a window and then dragged their thumb across the wet ink. The picture had a name that nobody remembers, and it does not matter very much. The cluster is catalogued as SMACS J, 0723.3-7327, which is a set of coordinates dressed up as a word, and everybody just calls it SMACS 0723. It sits in a small southern constellation called Volans, named by Dutch navigators in the late 16th century, after the flying fish they saw jumping alongside their ships. It has no bright stars. It has no mythology. Nobody has ever looked up at Volans and told a story about it, which is a strange thing to be true of the patch of sky where all of this begins. What matters is the number attached to the picture, and it is the number that most people skipped past on their way to admiring the colours. 12.5 hours. That is how long the telescope looked. Not 12.5 hours in one continuous stare either. The released image is a composite, built from separate exposures taken through several different filters and added together, and the total across all of them comes to 12.5 hours. Half a day. Less than the length of a long-haul flight. For comparison, the deepest image the Hubble Space Telescope ever produced, the ultra-deep field, took something on the order of 11 days of exposure spread across 400 orbits of the Earth, and astronomers argued about whether it was worth the time. In half a day, in the infrared, the new telescope went deeper. And then there is the second number, which is the one that gets quoted in every article, and which I think almost nobody actually pictures properly when they read it. The agencies described the patch of sky in the image as being approximately the size of a grain of sand held at arm's length by someone standing on the ground. Try that. Genuinely try it. Right now if you can, or in your head if you cannot. Pick up a single grain of sand. Hold it out at the full extension of your arm. Look at how much of the sky it covers. It covers essentially nothing. If you swept your arm across the sky, blocking out one grain of sand's worth at a time, you would be there for the rest of your life and you would not finish. I should say, because it matters later, that nobody has ever published a hard count of what is in that frame. The official descriptions say thousands of galaxies and they leave it there, and every specific number you have seen attached to that image was somebody's estimate rather than somebody's measurement. Hold on to that gently. It is going to come back. Inside that nothing, in half a day, the telescope found thousands of galaxies. Not thousands of stars, galaxies. Each one of those small smudges is a system of 100 billion stars or so, doing what our galaxy is doing, spinning slowly around its own centre, making new suns out of collapsing gas, and every one of those stars may well have worlds going around it. Thousands of them, in a grain of sand. That alone would have been enough. It would have been a perfectly good week for astronomy if the story had ended with a pretty picture and a nice statistic about how much universe fits into a very small space. But the picture was not chosen only because it was beautiful. It was chosen because of those bent streaks of light around the middle, and the bent streaks are where the trouble started. Those arcs are not a mistake in the optics, and they are not an artifact of the processing, they are gravity. The cluster in the centre of the frame contains an enormous amount of mass, hundreds of galaxies plus the dark matter binding them together, and mass curves the space around it. Light travelling through curved space follows a curved path. So light from galaxies far behind the cluster, galaxies that would ordinarily be far too faint for any instrument to register, arrives at the telescope smeared and stretched, and crucially, brightened. The cluster works as a lens. It is a lens nobody built and nobody can aim, and it does something no engineer can do at any price. It magnifies the early universe, which means that in that first image, on day 1, the telescope was already seeing past the cluster into objects that had emitted their light more than 13 billion years ago, when the universe was a few hundred million years old and had barely started assembling itself. And this is the part where the story stops being a celebration. Because when the people whose job it is to look past the colours started measuring the objects in that frame and the ones that followed in the weeks after, some of them did not look the way early galaxies were supposed to look. They looked too bright. They looked too organised. Several of them looked as though they had been running for far longer than the universe had given them. Within about 2 months, an object found in a related survey was being described in headlines as the most distant thing anybody had ever seen. A galaxy from barely 230 million years after the beginning. I want to tell you now, at the start, so that you know where this is going. That object is not where they thought it was. Not even close. The galaxy that was supposedly 230 million years old turned out to be sitting in a universe more than 1 billion years old, and the reason for the mistake is one of the most quietly unsettling things I've ever read about how we know anything at all. That is not a story about a telescope failing. The telescope has been, by nearly every measure, the most successful scientific instrument ever launched. It is a story about the last step, the step after the light arrives, after the detector counts it, after the numbers come out clean, the step where a number becomes a conclusion. Over the next couple of hours we're going to walk through what this thing actually found in its first 4 years, in order, and we're going to keep score honestly. Some of what it found survived every attempt to knock it down, and that material is stranger than anything the headlines managed to convey. Some of it did not survive, and the way it failed is a story in itself. But before any of that, I want to show you the machine, and I want to show you what it can do when the answer is not in doubt at all. Because you cannot appreciate how badly a measurement can go wrong at the edge of the universe until you have seen the same instrument, pointed a great deal closer to home, get an answer so clean that the world simply accepted it and moved on. Part 2. The machine and what it saw. Close to home. The telescope is a mirror 6.5 meters across, and it is not one mirror. It is 18 hexagonal segments of beryllium, each of them coated in a layer of gold about 100 nanometers thick, which across the whole array comes to roughly 48 grams of gold, less than you would find in a modest wedding ring collection, spread out over an area the size of a small room. Gold is there for one reason. It reflects infrared light better than almost anything else, and infrared light is the entire point. Those 18 segments had to be brought into alignment after launch, out in the cold, by a process of measuring the blur and nudging the mirrors and measuring again, until all 18 behaved as a single optical surface accurate to a few tens of nanometers. That process took months. It is why the launch happened in December of 2021, and the first picture did not appear until July of 2022. When the commissioning report finally came in, the optical performance was better than the requirement in essentially every category, which is not a thing that usually happens with instruments this complicated, and the science program was accelerated because of it. Underneath the mirror there is a sun shield the size of a tennis court, 5 separate layers of aluminium-coated plastic film, each layer about as thin as a human hair, held apart from each other so that heat radiates out sideways into space instead of passing through. On the sunward side of that shield the temperature is around 100 degrees Celsius. On the far side, it is around 230 degrees below zero. The difference across those 5 thin sheets is roughly 300 degrees, and that difference is what makes the whole mission possible, because an infrared telescope that is warm is a telescope looking at itself. The whole assembly sits about 1.5 million kilometers from Earth, on the side facing away from the Sun, at a point where the gravity of the Sun and the Earth combine in a way that lets a spacecraft keep pace with our planet as it goes around. That point is not actually stable. The telescope orbits around it in a wide loop and has to fire its thrusters every so often to stay there, and the fuel for those little corrections is what ultimately sets the end of the mission. Now, why infrared? The universe is expanding, and light travelling through expanding space gets stretched along with it. A galaxy that emitted ultraviolet light 13 billion years ago has had that light stretched over the whole journey into the infrared. By the time it reaches us, it is no longer the colour it left us. Hubble, which works mainly in visible and near ultraviolet light, simply cannot register most of it. And ground-based telescopes, however large, are looking through an atmosphere that is warm and full of water vapour, both of which glow in the infrared. It is like trying to photograph a candle through a window that is on fire. So the gap was real, and this instrument was built to occupy it, and the first thing worth understanding about the results is that when it points at something close and bright, the answers it produces are not in serious dispute by anybody. Let me give you the list, because it is a good list. In September of 2022, it turned to Neptune and produced the clearest image of that planet's rings in more than 30 years, and the first ever taken in infrared light. The last close look anyone had was Voyager 2, which flew past in 1989 and remains the only spacecraft ever to visit. In infrared, Neptune does not look blue at all. The methane in its atmosphere swallows red and infrared light so hungrily that the planet appears dark, almost charcoal, with bright patches where high-altitude methane ice clouds sit above the murk. 7 of its 14 known moons show up, and Triton, which reflects about 70% of the sunlight that hits its nitrogen ice surface, outshines the entire planet it orbits. In October of the same year, it watched a small body called Chariklo pass in front of a background star. Chariklo is the largest known centaur, an object about 250 kilometers across, wandering between the orbits of Saturn and Uranus, more than 2 billion miles from here. It also has rings, which nobody expected a body that small to be capable of holding, and which were discovered from the ground in 2013. The telescope did not photograph those rings. It could not. They are far too fine. What it did was record 63 separate measurements of the star's brightness as Chariklo crossed in front of it, and in that record there are brief dips just before and just after the main eclipse. Those dips are the rings. It is a measurement made entirely out of shadow. Separately, the spectra showed 3 absorption bands of crystalline water ice, which is quietly interesting, because radiation ought to scramble ice crystals over time, so something out there is resurfacing or grinding or colliding recently enough to keep making fresh crystal. In September of 2023, it looked at Europa and found carbon dioxide ice concentrated in one region of the surface called Tara Regio, a young, broken landscape of shattered and refrozen ice blocks covering something like 1,800 square kilometers. The concentration is the whole argument. If that carbon had been delivered by meteorites or manufactured by radiation, it would be spread evenly. It is not spread evenly. It is bunched where the shell has been disrupted from below, which means the carbon came up from the ocean underneath, and recently. That is the first real evidence that Europa's hidden ocean contains carbon, which is one of the things life requires. It does not say anybody is home, it says the water is chemically interesting. I should be precise about something here, because it gets misreported constantly. The companion paper published the same day searched for water vapour plumes venting off Europa, of the sort that had been tentatively reported before, and it found none. That is a null result, and it is stated as one in the title. This telescope has not photographed geysers on Europa. It looked, and there was nothing there to see, at least not that day. It did, however, see one somewhere else. Imagine standing on the south pole of Enceladus. You're on a moon about 500 kilometers across, which is small enough that you could drive around it in a day if there were roads. The ice under your boots is the whitest surface in the solar system. It throws back almost every photon that lands on it, which is why the ground is dazzling and the sky is still black. Cut into the ice near where you are standing are 4 long parallel fractures, hundreds of kilometers long, and out of those fractures, silently, continuously, water is coming. Not steam. There is no heat you can feel. The vapour leaves at about 25 degrees above absolute zero, colder than anything you have a word for, and it does not billow, because there is no air to billow into. It simply goes, in straight lines, upward and outward, and it does not stop. Follow it with your eyes. It rises past the height of the mountains you cannot see, past a distance equal to the width of the moon you're standing on, and then 10 times that, and then 20. It reaches out nearly 10,000 kilometers. The Cassini spacecraft flew directly through this plume, repeatedly for years, and never once saw its shape, because it was inside it. It took a telescope 1 billion kilometers away to see how big the thing actually was. About 300 litres of water leave that moon every second. Roughly 30% of it settles into a donut-shaped ring spread along Enceladus's orbit around Saturn. The other 70% escapes entirely and goes on to supply water to the whole Saturnian system. That little moon is where Saturn's E-ring comes from. It is quietly watering an entire planetary neighbourhood. There is more. In May of 2023, the telescope confirmed water vapour around a comet in the main asteroid belt, the first time anyone had ever done that, proving that primordial water ice can survive in a part of the solar system long assumed too warm to keep it, which matters a great deal if you're wondering how Earth got its oceans. And then it found the mystery. Comets typically carry something like 10% carbon dioxide among their easily evaporated material, and this one, 238P/Reed, has none that can be detected at all. Either it lost it over billions of years of sitting in the warm, or it formed somewhere the carbon dioxide never was. Out past Neptune it surveyed 54 icy bodies and found that carbon dioxide ice is essentially everywhere out there, and that the surfaces sort themselves into exactly 3 families: a water ice type, a carbon dioxide type, and an organics and methanol type that makes up about 1/3 of the sample. Those 3 families are almost certainly a record of where each object originally formed before Neptune migrated outward and flung them all into the orbits they occupy now. It is a fossil record written in frost. It took the first direct image of a planet around another star that any telescope had ever managed beyond 5 microns. It discovered a planet of its own, about the mass of Saturn, sitting in a gap in a dusty disk around a young star 110 light-years away, exactly where a planet had been predicted to be if something was carving that gap. And in February of 2026 it did something that I think is the cleanest single demonstration of what this machine is for. There was an asteroid. You may remember it. It was found on the 27th of December, 2024, 2 days after it had already sailed past us, and over the following weeks the calculated chance that it would hit the Earth on the 22nd of December, 2032, kept climbing. It peaked around the 18th of February, 2025 at roughly 3.1%, about 1 in 32. That was the highest impact probability ever recorded for an object that size, and the European Space Agency described it, in its own words, as the most dangerous asteroid discovered in the last 20 years. Then more observations came in, and the Earth risk collapsed to essentially nothing, about 1 chance in 20,000. But it did not disappear. It moved. The remaining wobble in the orbit still passed through the Moon. The lunar impact odds went from 1.8% to 3.8% after the telescope's first look to 4.3% after the second. And then the asteroid faded out of view, leaving that number hanging, and everybody assumed nothing more could be learned until 2028. An international team found 2 narrow windows in February of 2026 when the thing might just barely be detectable. Observations were made on the 18th and the 26th. It was one of the faintest targets the telescope has ever attempted, tracked against background stars whose positions were known to extraordinary precision thanks to a European mapping mission. And on the 5th of March, 2026, the agencies announced that the lunar impact was ruled out. It will pass the Moon by more than 20,000 kilometers. The same instrument also settled the argument about how big it is, because a rock's brightness in visible light confuses size with reflectivity. A small shiny rock and a large dark one look identical, but its heat output scales with actual physical area. In the infrared, the answer was between 53 and 67 meters across, about a 15-story building. Nobody disputed any of that. Nobody reanalyzed it and got a different number. The claim was made, and it was simply true. Hold that in your mind, because we are about to go a very long way from home, and the next thing this telescope measured was announced with just as much confidence, and it was wrong by a factor of more than 3. Part 3. The bump in the wrong filter. There are 2 ways to find out how far away a galaxy is, and almost everything that has gone wrong in the last 4 years lives in the gap between them. The first way is fast. You take a picture of a patch of sky through a series of filters, each of which admits only a narrow band of wavelengths, and you measure how bright each object is in each filter. Then you look for the place where the brightness falls off a cliff. In the early universe, there is a very reliable cliff. Neutral hydrogen floating between the galaxies absorbs everything shorter than a certain wavelength, so the light simply stops on one side of a line. That line is called the Lyman break. Find where the break sits in your filter set, and you know how much the light has been stretched, and therefore how long it has been travelling, and therefore how early in the history of everything the galaxy is. This is called a photometric redshift, and it is wonderful. You get it for thousands of objects at once out of a single image. It costs you nothing extra. It is how essentially every candidate for most distant galaxy ever gets identified in the first place. It is also, and I want to be careful how I say this, a guess. An educated, disciplined, defensible guess, built on real physics, but a guess from colours. None of this is new, incidentally, and that is worth saying because it protects the people who got it wrong. The technique dates back to the 1990s, when astronomers used exactly the same trick from the ground to find what they called Lyman break galaxies at a redshift of about 3. It has been used and checked and refined for 30 years. What changed with this telescope was not the method, it was the wavelength. At a redshift of 5, that break falls at around 3/4 of a micron. In light you could almost see. At a redshift of 16 it falls out near 2.1 microns, far out in the infrared, in a part of the spectrum where until 2022 nobody had a sensitive enough instrument to look at all. The second way is slow. You take the light from one object, spread it out into a full spectrum, and look for individual lines. Oxygen sitting at a wavelength you know, hydrogen sitting where hydrogen always sits, carbon in its place. Then you measure how far each of those lines has moved from where it should be. That is a spectroscopic redshift, and it is not a guess. It is a measurement. It costs enormously more telescope time per object, which is why you cannot do it for everything, which is why the guess exists at all. Although it is worth saying how hard the engineers worked to make the slow way faster. Inside the near-infrared spectrograph, there is a device called a microshutter array, roughly 250,000 tiny doors, each one about as wide as a human hair, each one openable and closable on command. Point the telescope at a crowded field, open the doors that happen to be sitting over interesting galaxies, leave the rest shut so their light does not contaminate anything, and you can take spectra of more than 100 objects at the same time. That is the machine that has been quietly cleaning up after the photometry for 4 years. It is not glamorous and there are no press releases about tiny doors. Now hold on to this, because here is the shape of the whole story. Nearly every headline between 2022 and 2024 that said the new telescope had broken, cosmology was built on the first method, and nearly every correction to those headlines came from the second. Let me show you one. In the summer of 2022, in a survey of a different patch of sky, an object turned up that the photometry placed at a redshift of about 16. 16 is enormous. 16 would put the galaxy roughly 230 million years after the Big Bang, which is to say in the first 1.5% of the universe's life. The papers went out. The coverage followed. For a few months, the most distant object anybody had ever seen had a catalogue number and a place in the sky. Then somebody pointed the spectrograph at it. The answer came back at 4.912, not 16, under 5. The galaxy is real, it is genuinely far away, and it is sitting in a universe about 1.2 billion years old rather than 230 million. It is not from the dawn of everything, it is from the adolescence. I want to be very specific about how that happened, because it is not carelessness, and it is not fraud, and it is not anything you can dismiss. It is much more interesting than that. Follow one photon, it leaves a galaxy that is busy making stars, and because it is busy making stars, that galaxy is full of hot gas glowing at very particular wavelengths, doubly ionized oxygen, hydrogen shining in the line we call hydrogen alpha, the ordinary emission of any energetic nursery. The photon travels for billions of years. Space stretches underneath it the whole way, and the photon stretches with it, so by the time it arrives here it is no longer the colour it was when it left. It falls into a mirror 6.5 meters across, bounces 4 times through the optics, passes through a filter that admits light between roughly 2.4 and 3.1 microns, and lands on a detector, where it becomes one count. Add up all the counts. Now you have one number. Do it in 5 filters and you have 5 numbers. Plot them side by side, and there it is. 4 of the points sit in a line, and one of them sits higher than the others. That is the whole claim, not a picture of a galaxy at the edge of time, a bump in a graph. The trouble is that a bump in a graph has more than one cause. A Lyman break makes a bump because everything on one side of it disappears, but a very strong emission line landing inside a filter also makes a bump because that one filter is catching extra light the others are not. 2 completely different things, at 2 completely different distances, produce a shape that looks the same when all you have is 5 numbers, and the emission lines in this particular galaxy were not subtle. Oxygen and hydrogen were pouring out of it at a rate that can lift the measured brightness in a single filter by tens of %. That is more than enough. In a 5-point graph, tens of % in one point is the difference between a galaxy in the adolescent universe and a galaxy from before there were supposed to be galaxies. None of this was a surprise in principle. Before the telescope ever launched, theorists had written papers warning about exactly this. Dusty, line-bright galaxies at moderate distance masquerading as pristine ones at extreme distance, and they had even estimated how often it would happen. The word for them in the literature is interlopers. Everyone knew they were coming. It is simply that when the picture arrives and one object is sitting further out than anything anybody has ever recorded, the human response is not to assume it is an interloper. There is a mirror image error too, and it is worth a moment because nobody ever writes about it. Genuinely distant galaxies can be missed entirely because they are faint in every filter and there is no bump to notice. The frontier of any survey is not a clean edge. It is a smear, populated by the objects whose measurements happen to scatter high, and thinned out by the objects whose measurements happen to scatter low. That is not a flaw in anyone's work. It is what the edge of an instrument's ability looks like from the inside. The paper that settled it has a title that says it out loud: Confirmation and Refutation of Very Luminous Galaxies in the Early Universe. Confirmation, plural, of some. Refutation of others. Both in the same sentence, which is about as honest as a title gets. And in fairness to the field, this matters. The same spectroscopic campaigns went and checked the other candidates too, and plenty of them held up. One team confirmed 25 galaxies with real, measured redshifts running from 8.61 all the way to 13.20. The survey was not producing nonsense. It was producing a mixture, and there was no way to tell from the picture alone which was which. You would think a story like that would arrive as a relief. The universe is not broken, we just miscounted. Everybody go home. It did not work out that way. The correction that came next did something considerably worse than the mistake it fixed. Part 4. 6 galaxies that were too heavy. In February of 2023, a paper appeared in Nature describing 6 galaxies, and the press called them universe breakers. The paper did not call them that. The paper called them candidates, and it put the word in the title, which is a detail that vanished somewhere between the journal and the news cycle, and has never really come back. Here is what it said. In the first data from one of the big early surveys, there were about 13 objects, sitting at redshifts around 8, which is to say roughly 600 million years after the beginning, that appeared to contain more than 10 billion times the mass of the Sun in stars. 6 of them were flagged as particularly solid, and one of them looked like it might hold something near 100 billion solar masses of stars, which is a Milky Way. A fully grown, present-day, ordinary spiral galaxy's worth of stars, assembled and shining, when the universe was 4% of its current age. If that were right, it would be a genuine problem. Not a problem for the Big Bang, which people constantly claim, and which we will deal with properly later, but a problem for our understanding of how quickly gas can fall together and turn into stars. Matter has to collect. It has to cool. It has to collapse. There is a speed limit built into gravity and into the amount of stuff available, and 100 billion solar masses in 600 million years pushes hard against it. So the obvious question is, how do you weigh a galaxy that is 13 billion light-years away? You do not, is the honest answer. Nobody has ever weighed a distant galaxy. What you do is measure its colours in several filters, and then fit a model to those colours. A model that says, in effect, if this light came from a population of stars, and if those stars formed at roughly this rate over roughly this period, and if there is roughly this much dust in front of them reddening everything, and if stars in the early universe come in roughly the same range of sizes they do today, then the total mass required to produce this much light is such and such. Count the ifs. There are 4 of them in that sentence, and each one is a modelling choice. Change just one, the assumption about how many massive stars form relative to small ones, and the answer can move by a factor of several. If the first generations of stars were systematically heavier than stars are now, then a given amount of light corresponds to far fewer stars and far less mass, and the problem shrinks without a single galaxy changing at all. It is also worth being precise about what the standard model of cosmology actually forbids here, because it is narrower than people assume. Nothing in the theory says a big galaxy cannot exist early. What the theory does is tell you how much matter has managed to clump together into gravitationally bound structures by a given moment, and then the question becomes what fraction of that available gas turned into stars rather than sitting around uselessly as gas. In the universe we can see nearby, that fraction is not close to 1. Galaxies are wasteful. Star formation is inefficient, because the first stars to form blow the surrounding material apart before the rest of it can collapse. So the objection was never that these galaxies were impossible. The objection was that they required almost every available atom to have been converted into stars with nothing wasted, which is not how anything else in the universe behaves. And the most conservative escape from that objection is simply that the early universe was better at it. Denser gas, closer encounters, less time for anything to blow itself apart before the next collapse got going. There is a proposed regime, the phrase in the literature is feedback-free starburst, in which the densest early clouds convert gas into stars faster than the first supernovae can clear the room. Several sets of simulations run between 2024 and 2026 reproduce the observed number of bright early galaxies under exactly that assumption, with no new physics required at all. And pleasingly, that same mechanism would naturally produce a violent burst followed by an abrupt shutdown, which is going to matter enormously in about half an hour. But that is not what actually happened here, and what actually happened is better. They went back with the spectrograph. 6 of the 13 got real spectra, and the redshifts held. These objects are genuinely where the photometry said they were. Early, seriously early. That part survived. The masses did not. Because when you look at the spectrum rather than the colours, you can see the shape of the individual emission lines, and in at least one of these objects, a source with the unlovely name C-13050. The hydrogen beta line is not sharp. It is smeared out across something like 1800 kilometers per second. Gas does not move at 1800 kilometers per second because it feels like it. Gas moves at 1800 kilometers per second when it is whipping around something extremely compact and extremely heavy at close range. That line shape is the classic signature of matter falling into a black hole, which means part of the light that was being counted as starlight is not starlight. It is the glow of an accretion disk, and if you subtract that, the inferred stellar mass falls, and the conflict with cosmology largely evaporates. Everybody go home then. Except. Think about what has just been said. The reason these galaxies do not contain an impossible number of stars is that a large fraction of their light is coming from gas, spiralling into a supermassive black hole, 600 million years after the universe began, which means that at 600 million years there were already black holes big enough and hungry enough to outshine the galaxies around them. That is worse. That is much worse. A black hole that size is not a thing you can grow quickly. If it started as the corpse of an ordinary massive star, 10, maybe 100 times the Sun, then to reach millions of solar masses, it has to eat continuously, at the absolute physical maximum rate, without pausing, for essentially the entire time available. And the physical maximum rate is a real limit, not a bureaucratic one. Material falling in radiates so fiercely that the radiation pressure pushes the remaining fuel away. A black hole feeding at full speed tends to blow out its own dinner. So the crisis did not go away when the mistake was found. It relocated. It stopped being a story about galaxies being too big and became a story about black holes being too big, too soon, which is a considerably harder question with considerably fewer available answers. I find this genuinely unsettling in a way the original headline never was. We are used to the idea that when a scientific claim gets checked, the checking makes the world smaller and tamer. The sea monster turns out to be a whale. The ghost turns out to be a draft. Here the checking made the world stranger. The correction was the bad news. And there is one more thing about those red, compact objects, which nobody knew at the time. Blue in the shorter wavelengths, red in the longer ones, so small that in the long wavelength images they look like single points rather than anything with a shape. That combination did not have a name in 2023. It has one now, and the argument about what those objects actually are has not been settled. It has multiplied. We will get there, but first there is a galaxy I need to tell you about, because it is the one that survived every correction anybody could throw at it, and it contains something it has no business containing. Part 5. Oxygen, where there should not be any. The record for the most distant galaxy has changed hands 3 times since this telescope opened its eyes, and each time it has changed hands, the reason has been a spectrum rather than a picture. The first was found on the 29th of September, 2022, in imaging from a survey designed specifically to stare at one patch of sky for a very long time. Spectroscopy the following month confirmed it at a redshift of 13.2, about 325 million years after the beginning. Light that has been travelling for 13.6 billion years. It held the record for a year and a half. Then, on the 30th of May 2024, the agencies announced 2 more, and one of them was further out than anything before it. The number they gave at the time was 14.32. That number is now wrong, and the way it became wrong is one of my favourite small stories in modern astronomy, because it is the exact opposite of everything else in this video. A completely different observatory. A radio array sitting on a plateau in the Chilean Andes at 5,000 metres, made of 66 separate dishes, working at wavelengths 100 times longer than the ones the Space Telescope uses, went and looked at the same object, and it found a single, clean, unmistakable line, doubly ionized oxygen, emitting at a wavelength of 88 microns in its rest frame, stretched by the expansion of the universe into the millimetre range by the time it arrived. From that one line, the redshift comes out at 14.1793, plus or minus 7/10,000ths. Look at that precision. Not 14.3, not about 14. 14.1793. 2 different observatories, on 2 different continents, well, 1 continent and 1 point in space, using 2 completely different techniques at wildly different wavelengths, converging on the same object and pinning it to 4 decimal places. That is what a confirmed result looks like, and I want you to keep the taste of it in your mouth, because we are going to spend a long stretch of tonight looking at results that never got this. So, 290 million years after the universe began, by the agency's own reckoning, when everything was 2% of its present age. The galaxy is small. Half its light comes from within about 260 parsecs of the centre, which is to say 850 light-years or so, against the 100,000 light-years of our own galaxy's disk. It is making stars at something like 8 solar masses a year, which sounds modest until you remember how little of it there is, and crucially it is resolved. The telescope can see that the light is spread out. It is not a point. Whatever is glowing, there is glowing across a real, measurable extent, which rules out the possibility that we are looking at a single, bright object pretending to be a galaxy. There is also something quietly informative in the shape of the break at the blue end of its spectrum, the cliff we talked about earlier. In this galaxy it is extremely sharp. The light does not fade out across a range of wavelengths, it stops. That sharpness is itself a measurement of the universe the galaxy was sitting in. It means the hydrogen filling the space between galaxies at that moment was still overwhelmingly neutral, still opaque, not yet burned transparent by the ultraviolet output of the first generations of stars. We are not just seeing an early galaxy, we are seeing it through a fog that had not lifted yet, and it is worth pausing on how quickly all of this arrived. In 2016, the Hubble Space Telescope found a galaxy at a redshift of 11.1, and at the time that was widely discussed as being somewhere near the practical limit of what any instrument was ever likely to reach. It sat there as the record, unbeaten, for 6 years. This telescope passed it within months of switching on, and then kept going, and the objects it found beyond that line are not faint smudges scraping the edge of detection. Several of them are bright, and then there is the oxygen. I have been saying it casually, the oxygen line, the oxygen emission, as though it was simply the tool used to get the number. It is not. It is the headline. The oxygen is the discovery. Here is why. When the universe began, it made hydrogen and helium and a whisper of lithium, and that is essentially the entire menu. Nothing else. No carbon, no nitrogen, no oxygen, no iron, no silicon. Nothing you or I are made of. Every heavier element in existence was manufactured inside a star, by fusion, under pressures nothing else in nature produces, and then thrown back out into space when that star died. So oxygen in a galaxy is a receipt. It is proof that stars have already lived there and finished and exploded and had their contents stirred back into the surrounding gas, and that new stars have formed out of that enriched material, all of which takes time. The measured abundance is around 6% of the sun's, which does not sound like much, but it is roughly 10 times more heavy elements than the models expected to find at that moment in cosmic history, and the observatory that made the measurement said so in exactly those words in its own announcement. 290 million years. In that window, an entire generation of massive stars had to condense out of pristine hydrogen, ignite, burn through their fuel, which massive stars do fast in a few million years rather than the 10 billion our sun is good for, die violently, scatter their manufactured elements across hundreds of light years, and have that debris cool and settle and mix into the gas that formed the next generation, the one we are currently looking at. The universe did not wait. That is the sentence I keep coming back to with this object, and I want you to hold on to it, because we are going to need it again. Nobody handed the early universe a schedule. It did not build slowly and cautiously toward complexity, while the models watched approvingly. It got on with it, at a pace that every model we had built quietly assumed was unavailable, and it did so in the dark, before there was anything transparent enough for the light to travel through cleanly. And I want to make this personal for a moment, because it is easy to let a number like 6% of solar float past as an abstraction. Take a breath. Go on, an ordinary one. About a fifth of what just went into you is oxygen, and none of those atoms were made on Earth. They were made in the cores of stars that died before the sun existed. That process, hydrogen to helium to carbon to oxygen, then a supernova to distribute it, is the same process, running by the same rules, that this galaxy was already running 290 million years after the beginning of everything. The universe was making the stuff you're made of before it had finished making galaxies. One clarification, because this gets muddled constantly, and I would rather be boring than wrong. There is a famous chemical anomaly among the very early galaxies involving nitrogen, an object at redshift 10.6 with far more nitrogen relative to oxygen than anything should have, which has driven a whole speculative literature about supermassive stars and the formation of globular clusters. That is a different galaxy. Do not let anyone attach the nitrogen story to this one. This one's anomaly is oxygen, and oxygen is quite enough. There is a third record holder found more recently, and it is further out still. But what I find remarkable about it is not the distance. It is the name the team gave to the survey that found it, because they wrote their own doubt into it, before they knew the answer. Part 6. Mirage or Miracle. Somebody, at some point in the planning of a survey, had to sit down and give the thing a name. Surveys usually get named the way government programs get named, an acronym reverse-engineered from a phrase that nobody would ever say out loud. This one is called Mirage or Miracle. That is not a joke, and it is not marketing. It is a statement of the problem, written into the title of the project before the project had any results, by people who had watched what happened to the last round of record-breaking candidates and had decided to be honest with themselves in advance. Every bright dot at the edge of the data is one of two things. It is a miracle, a real luminous galaxy from an era when there should not be luminous galaxies, or it is a mirage, a nearer object wearing the colours of a further one, exactly like the one that fell from 16 to 5. The survey went looking, and it found something. The object is catalogued as MOM-Z14, and its spectroscopic redshift is 14.44. As of tonight, in August of 2026, it is the most distant galaxy anybody has ever confirmed. The timeline is worth walking through, because it shows you the difference between how a claim was made in 2022 and how one gets made now. The candidate was picked out of imaging first, the fast method, colours in filters, a promising bump. That is where the old story would have ended, with a press release. Instead, the team applied for time, got it, and pointed the telescope at the thing directly in April of 2025. The imaging came on the 16th of May, then the spectrograph. And what came back was not a single ambiguous feature. It was a sharp Lyman break. That cliff again, the wall of neutral hydrogen, sitting exactly where a redshift of 14.44 says it should sit. And in addition, 5 separate emission lines in the ultraviolet part of the spectrum, each detected at around the 3 sigma level, each landing at its own predicted wavelength. 5 lines, all in the right places. That is not a bump in a graph, that is a fingerprint. The preprint circulated in May of 2025, and the paper was published in January of 2026. The galaxy sits about 280 million years after the beginning of everything. It is worth taking a moment on what 280 million years actually means, because the number is so large in ordinary human terms that it can slide right past you. It is longer than there have been dinosaurs. It is longer than there have been flowering plants. 280 million years ago on Earth, all the land on the planet was fused into a single continent, and the first mammal-like animals were just getting started. That entire stretch, the whole span from before the dinosaurs to now, is the total amount of time this galaxy had, from the beginning of the universe to exist at all, and in that time it collected enough gas, made enough stars, and got bright enough that 400 generations of a species that did not exist yet would eventually build a machine capable of seeing it. There is one number attached to this galaxy that trips people up every time, and it is worth 30 seconds. Coverage of the discovery quoted its present-day distance as something like 33.8 billion light-years, and the immediate objection is obvious. The universe is only 13.8 billion years old, so how can anything be 33 billion light-years away without the light having outrun its own start? The answer is that the light did not have to cross 33 billion light-years. It crossed a much shorter gap, but while it was in transit, space itself was stretching underneath it, carrying the galaxy that emitted it steadily further away. The light took about 13.5 billion years to arrive. The galaxy that sent it, if it still exists in some form, is now roughly 33 billion light-years off, and we will never see what it looks like today. Nothing broke a speed limit. The road just got longer while we were walking it. Now here is where the story gets quieter and, to me, more interesting. Since MOM-Z14 was confirmed, nothing has beaten it. In January of 2026, another galaxy was confirmed, from imaging taken back in 2023 as part of a program that piggybacks on other observations, pointing wherever the telescope happens not to be pointing. That one came in at 13.53, about 310 million years after the beginning, and it is described in the literature as the 4th most distant galaxy known, which is a small phrase doing a large amount of work, because it tells you independently that in the year and a half since, nobody has slipped anything past 14.44. It is a large galaxy by the standards of its era, and unusually bright in the ultraviolet. Among everything confirmed beyond redshift 10, only one object outshines it. It sits in the constellation Aquarius, which you can find on any clear autumn evening, and which contains, invisibly, one of the oldest things in the catalogue. And there is a further piece of evidence published in 2026 from a search that swept more than 6/10 of a square degree of imaging, a serious area by the standards of deep surveys, looking for the earliest galaxies it could find. Its conclusion was that star formation drops off rapidly beyond a redshift of about 12. Not that the telescope stops being able to see, that there stops being as much to see, which would mean the frontier is not a limit of the instrument. It is a real edge in the universe, the point where galaxy formation was genuinely just getting started, and the things that existed were few and far between. If that holds, MOM-Z14 may sit at the top of the list for quite a while, not because we cannot look further, but because there is not much further to look. So let us take stock. The record fell 3 times, and each time it was confirmed by spectroscopy, rather than announced from colours. A galaxy at 290 million years contains 10 times more heavy elements than it should. 6 galaxies that looked impossibly massive turned out to be genuinely early, but partly powered by black holes that are themselves impossible. And the field has become careful enough that it now names its surveys after its own uncertainty. That is the state of the early universe as measured, and it is already stranger than the headlines managed. But there is a category of object I have been putting off, and I have been putting it off because it does not fit into any of the boxes I have been using. They are not galaxies exactly. They are not quasars exactly. They were invisible to every telescope that came before this one. They are everywhere in the data now, and at the last count there were more than 6 mutually incompatible explanations for what they are. All of them live, all of them defended by serious people, some of them published within a week of each other. Part 7. The dots that should not be there. They are called little red dots, which is possibly the least dramatic name ever attached to a genuine crisis in astrophysics, and I would like to walk you through what makes them so difficult, because the difficulty is not the usual kind. Usually, when astronomers say they do not understand something, they mean they cannot explain a detail. They know it is a star, they cannot explain the flickering. They know it is a galaxy, they cannot explain the shape of the arms. That is normal science, and nobody loses sleep over it. This is not that. With these objects, the question is not why does it behave that way. The question is what kind of thing it is. Here is what we can say for certain, because it is measured. They are compact. In the long wavelength images they appear as points. No structure, no extent, nothing you could call a shape. They are red, extremely red, but with a peculiar twist. In the shorter wavelengths, corresponding to ultraviolet light in their own frame, they turn blue again. Plot brightness against wavelength and the line comes down, turns, and goes back up. The shape has a nickname in the literature. They call it the V. They cluster at redshifts of roughly 4 to 9, which is to say between about 600 million and 1.5 billion years after the beginning. They appear to peak in abundance somewhere around redshift 6 and to have largely vanished by redshift 3, which means whatever they are a phase and not a permanent feature. And they were essentially invisible to Hubble. There are hundreds of them in the new data. There were none in the old data because the old data could not reach the wavelengths where they live. Then there are the emission lines, and this is where it starts to hurt. Many of them show lines that are broad. Not slightly broad, thousands of kilometers per second broad. And in every other context in all of astrophysics, that width means one thing. Gas moving very fast, in a small volume, around something extremely heavy. It means a black hole with a disk around it. Fine then. They are early quasars wrapped in dust which reddens them. Case closed, everybody home, except they are X-ray weak. A black hole eating at that rate should blaze in X-rays. That is what accretion does. And a large fraction of these objects have been looked for in X-rays and are simply not there, or are far dimmer than they ought to be. Worse, if they were dust reddened, the dust would absorb all that energy and re-radiate it as heat in the mid-infrared. And they are faint there too. Dust that reddens something has to glow. These do not glow, so the object has the kinematics of a black hole and none of the energetics, and that contradiction is the entire reason the argument exists. Let me give you the state of that argument as of this month, and I want you to notice the dates. There is a large spectroscopic census, published in 2025, whose subtitle is essentially its conclusion. Every point source with the V-shaped continuum has broad lines. Every one. That is a strong result, and it pushes hard towards something spinning around a black hole. There is a school of thought, and this is the one that has been gathering momentum, that says these things are neither stars nor black holes but a hybrid that nobody has ever seen. The phrase being used is black hole star. The idea has an ancestor. Theorists proposed something called a quasi-star back in the mid-2000s. A black hole seed sitting at the center of an enormous envelope of gas held up by its own radiation, and for the better part of 15 years it was a solution with no problem attached to it. There is a competing school which says there is no black hole at all, that each of these objects is a globular cluster in the act of forming, dominated by one enormous short-lived star, and that the strange spectrum comes from the star and the density of the gas around it. That paper came out in June of 2026. And then there is a third position, published in 2 studies on the 5th of August, 2026, 12 days ago as I record this, arguing that pulsating supermassive stars, around 100,000 times the mass of the Sun, can produce all 3 of the defining features at once, with no black hole required either. There are further options in the literature that I will mention only in passing, because they are long shots and everybody knows it. Collapsed supermassive dark stars, and compact starbursts evolving into early black holes, and there is a recent result finding what look like nearby cousins of these objects at much lower redshift, which would be enormously useful, because it would mean we could study the population without the distance. 6 or 7 distinct frameworks, all published, all alive, nobody in a position to close the question, and then, on the 12th of August, 2026, 5 days ago, a paper appeared in Nature describing a single one of these objects in detail and arguing that it belongs to a class of thing that has never been observed before. I want you to try to picture it, and I should warn you that your intuitions will not help. You are approaching a black hole star. From a distance, through a telescope, it looked like a star's spectrum. the continuous glow of something hot and dense with lines in it. So you expect a star. As you close in, the thing resolves, and it is not the size of a star. It is the size of a solar system. If you dropped it into our own, the outer edge of it would be somewhere out past the giant planets. There is no surface. There is a fog, thickening as you descend, gas so dense that light entering it does not travel. It staggers, absorbed and re-emitted 100 billion times before it finally works its way out, so that a photon released near the centre takes an eternity to reach the edge and arrives having entirely forgotten where it started. And down at the bottom of that fog, buried at the centre, is a black hole with 100,000 times the mass of the Sun. The whole structure, viewed from outside, is pouring out energy at something like 100 billion times the maximum any star is physically capable of producing, and it looks, from here, like a small red point. The object has a designation. It came out of the same Mirage or Miracle survey that found the distance record, and it is described as the earliest known black hole star sitting at cosmic dawn. The proposal is not that we have found one interesting object. The proposal is that this is the engine inside all the little red dots, a single answer to a question hundreds of objects have been asking since 2024, and the scale mismatch inside that object is worth one more sentence, because it is the strangest part. A black hole of 100,000 solar masses has an event horizon roughly 300,000 kilometers across in radius, less than the distance from here to the Moon, so the actual black hole at the center of this thing would fit comfortably inside the orbit of our own satellite, and the glowing envelope around it spans a planetary system. Nearly all of what you would be looking at is gas. It might be right. It is the strongest single object case anybody has made, and it matters more than one object should, because current estimates suggest these dots make up a substantial share of everything actively feeding in the universe beyond redshift 5. Whatever they turn out to be, they are not a footnote, but hold the dates in your head. The pulsating star papers came out on the 5th of August. The black hole star paper came out on the 12th. Two mutually incompatible explanations for the same population, 1 week apart, both in serious venues, both by people who know exactly what the other camp is arguing. That is not a field in trouble. That is a field with more data than theory, moving fast, in public. And while all of that is being fought over, there is a much quieter anomaly sitting in the same data that almost nobody talks about. A galaxy that did the opposite of everything we have discussed so far. It did not burn too bright. It stopped. Part 8. The Galaxy that Fell Asleep. Let us step back for a moment and put the pieces on the table together, because we are about halfway through and the shape of the thing is starting to show. A telescope opened its eyes in the summer of 2022. In half a day, on a patch of sky the size of a grain of sand held at arm's length, it found thousands of galaxies. Within weeks it produced a candidate for the most distant object ever seen, and that candidate turned out to be sitting in a universe 5 times older than advertised, because a bright emission line had landed in the wrong filter and made a bump. Then 6 galaxies appeared that seemed impossibly heavy, and when the correction came in, the mass problem dissolved and a black hole problem took its place. Then a galaxy 290 million years old turned out to be full of oxygen, which requires a whole generation of stars to have already lived and died. Then a record fell to something at 14.44, confirmed 5 separate ways, and then hundreds of small red points appeared in the data that nobody can classify, with at least 6 live explanations and 2 of them published a week apart this month. That is the ledger so far. Everything in it is about things happening too fast, too early, too bright. Now here is one that goes the other way. The object is a galaxy found in the same deep survey that produced 2 of the distance records. Its redshift is 7.29, which places it about 700 million years after the beginning. And when the spectrum came back, in a paper published in Nature on the 6th of March, 2024, it showed 2 things. The first was an absence. There were no emission lines, none of the bright, hot signatures that come from gas being lit up by newborn stars. Whatever ionizing radiation had been in that galaxy, it had stopped. The second was a presence. There was a feature called a Balmer break, a step in the spectrum caused by hydrogen-absorbing light in the atmospheres of a particular class of star. Those stars, the A-types, are hot and white, and they live for a few 100 million years to 1 billion, which is a blink by stellar standards, but an eternity compared with the giants. When a galaxy's light is dominated by them, it means the most massive stars, the ones that live and die in a few million years, are already gone. Burned out. Finished. Put the two together, and you have a galaxy that made stars and then stopped, and has been sitting there since with an aging population and nothing new coming through. The technical word is quiescent. The word the coverage used was dead. You can read the whole history straight off the spectrum, which I find remarkable in itself. There was a burst of star formation. It was intense, and it lasted somewhere between 30 and 90 million years, briefer than the time between us and the last dinosaurs, and then starbirth stopped abruptly. Not tapered. Stopped. The galaxy is not large. It is comparable in mass to the small Magellanic Cloud, which is the smaller of the two companion galaxies you can see with the naked eye from the southern hemisphere on a clear night, hanging there looking like a detached piece of the Milky Way. A few 100 million suns worth of stars. A dwarf. And that is precisely why it is a problem. Because there is a standard list of things that can shut down star formation in a galaxy, and at 700 million years, not one of them is available. A supermassive black hole at the centre can do it, blasting the gas out with radiation and jets. But this galaxy is far too small to host one big enough to matter. Supernovae can do it if enough massive stars die at once, and the combined pressure drives the gas out past escape velocity. And that is at least plausible here, because a small galaxy has weak gravity, which is exactly why the same mechanism cannot quench a big one. The gas supply can simply run out, but at 700 million years the universe is drowning in hydrogen. Nobody has run out of anything. Or the galaxy can fall into a rich cluster and have its gas stripped away by the pressure of moving through the surrounding medium. But there are no rich clusters yet. They have not had time to assemble, so whatever shut this thing down worked faster and at lower mass than any model was built to allow. And I want to sit with this one for a moment, because it is a small thing, and it is easy to skip past on the way to the black holes. 700 million years after everything began, in a universe that had barely started, there was a modest collection of stars that flared into life, made everything it was ever going to make in a window shorter than the age of the Atlantic Ocean, and then went quiet. Not violently. Nothing exploded that we can see. It simply stopped, and the stars it had already made carried on aging, the bright ones going first, the rest cooling toward red, the whole thing dimming. We caught it at that moment. The light we're reading left it while it was still in the early part of that silence. There is a phrase in the paper that almost never survives into the coverage, and it is the phrase that keeps this from being a tragedy. The authors describe the galaxy as quenched, and then they add carefully, temporarily or permanently. Because in the early universe, small galaxies may not die. They may gasp. A burst of star formation blows the gas out beyond the galaxy's feeble grip. Star formation stops because there is nothing left to collapse. And then, over tens or hundreds of millions of years, gravity slowly hauls that gas back down and the whole thing starts again. There is a body of theoretical work on exactly this, with titles like Dead or Alive, arguing that what looks like a corpse may be a galaxy holding its breath. Which is a lovely thought and also a slightly haunting one, because if that is common, if a meaningful fraction of early galaxies are switched off at any given instant, then every survey that has ever counted star-forming galaxies at these distances has been systematically missing some of them. The census is short by an unknown amount, and the amount is unknown because the things we're failing to count are, by definition, the ones not shining. The universe did not wait, and I said earlier that I would need that sentence again. Here is the second edge of it. The same haste that assembled things early also finished them early. It did not wait to start, and it did not wait to stop. There is no phase in any of this where anything takes its time. So far, everything I have described has been a fight about objects. How far, how heavy, how old, what kind. But there is a second front, and it is stranger, because on this one the telescope was pointed at something much simpler than a galaxy. It was pointed at the direction things spin. Part 9. The direction nobody ordered. Almost everything in modern cosmology rests on an assumption so basic that it usually goes unstated, which is that the universe has no preferred direction. There is a name for it. The cosmological principle. It comes in two halves. Homogeneity says that on large enough scales, one region of the universe is much like another. No centre, no special place. Isotropy says that on large enough scales, one direction is much like another. No axis, no orientation, nothing that distinguishes up from down at cosmic scale. Take those away, and an enormous amount of the mathematics stops working. Not because the mathematics is fragile, but because it was built assuming symmetry, and asymmetric versions of it are far harder and far less constrained. In February of 2025, a paper appeared in the monthly notices of the Royal Astronomical Society reporting an asymmetry. The method is straightforward enough to explain in a sentence. Take the deep field images, find every galaxy in them that shows spiral structure clearly enough to tell which way the arms wind. Classify each one as clockwise or counterclockwise as seen from Earth. Count. 263 galaxies had spiral structure clear enough to classify. Of those, 158 turned one way, 105 turned the other, roughly a 60-40 split, where you would expect 50-50, and the reported statistical significance was about 3.4 sigma. The classification was not done by eye, and it was not done by a machine learning system trained on human judgments, which matters, because both of those methods have been accused of importing human bias. It was done by a piece of software that converts each galaxy image into a plot of brightness as a function of radius and angle, and reads the curvature of the arms directly off the shape of that plot. It is deterministic. Run it twice and you get the same answer. Mirror the image and you get the mirrored answer. That symmetry is the author's central defense, and it is a fair one. Now. There are two explanations on the table, and I want to give you the exciting one first, only so that I can then take it away from you. The exciting explanation is that the universe was born rotating. The author's own words are worth quoting because the phrasing is precise and the coverage was not. One explanation, he wrote, is that the universe was born rotating, and that explanation agrees with theories such as black hole cosmology, which postulates that the entire universe is the interior of a black hole. That is a real theoretical proposal, incidentally, and I want to be fair to it. It comes out of work on a version of general relativity that includes torsion as well as curvature, and in that framework, collapsing matter inside a black hole does not necessarily end in a singularity. It can rebound, and if it rebounds, what happens on the inside looks, from the inside, like a new expanding universe. If our universe formed that way, inside a parent black hole that was itself rotating, it would inherit some of that angular momentum. There would be an axis. Galaxies forming in that space might preferentially align with it. If that were established, it would be the largest thing anyone has ever discovered. It is also, and I want to be blunt, not established. Here is the second explanation, which is the one the author of the paper himself thinks is more likely. We are not standing still. The Sun goes around the centre of our own galaxy at roughly 220 kilometers per second, which is about 0.07 of 1% of the speed of light. That sounds negligible. But a galaxy out there that happens to be rotating against our direction of motion is very slightly brighter from where we sit than one rotating with it, because of Doppler shift. And every deep survey ever conducted is limited by brightness. You see the things above your detection threshold and you miss the things below it. So if one-handedness is very slightly brighter, one-handedness is very slightly more likely to make the cut. That would produce exactly this signal, and it would have nothing whatsoever to do with the structure of the universe. But watch what happens when you follow that explanation all the way down, because there is a sting in it. If our own motion is systematically biasing how bright distant galaxies appear, then that bias applies to everything, not just to spirals, not just to handedness. Every measurement of a distant object's brightness would need a correction, and brightness is how we estimate mass and how we estimate distance. The boring explanation is not actually boring. It says there may be a small, uncorrected error threaded through the entire catalogue of deep sky measurements, which would feed straight back into the question of whether those early galaxies really are too massive. The university's own press release framed it in exactly that flat, careful way. The rotational velocity of the Milky Way should be factored into deep space observation. No black holes, no birth of the cosmos, just a correction. And now the part that the viral version of this story never includes. Other teams do not find the asymmetry at all. A study published in 2024 applied a different statistical approach to the question of galaxy spin directions, and concluded that the distribution is random. An earlier analysis argued that previously reported asymmetries came from duplicate objects, the same galaxy appearing twice in overlapping survey regions and being counted twice. The author of the new work has published responses on both points, and the dispute has not been resolved. Beyond that, there are structural problems that anybody would raise. 263 galaxies is a very small number, on which to hang a statement about the structure of everything. 3.4 sigma is well below the 5 sigma threshold that physics conventionally demands before calling something a discovery. 5 sigma is roughly a 1 in 3.5 million chance of being a fluke. 3 sigma is about 1 in 370, and the gap between those two is where a great many exciting results have quietly gone to die. And the selection step is a real concern. Somebody has to decide which galaxies show spiral structure clearly enough to classify, and faint and edge-on galaxies get excluded, and it is not obvious that the exclusion is neutral with respect to handedness. It also is not the first time. In the mid-2000s, analysis of the oldest light in the universe turned up what people started calling the axis of evil, an apparent alignment in the large-scale pattern of the cosmic microwave background that should not have had any preferred direction either. It was argued about for years. It never reached consensus, and it never quite went away. Claimed violations of isotropy have a long history of being real in the data and ambiguous in their cause. So where does that leave it? It leaves it where the field has left it, which is unresolved and mostly regarded with polite skepticism. The claim has been made by one researcher over a decade across several datasets, and he has been consistent and open about his methods. Other researchers looking at similar data find nothing. The consensus is that there is no consensus. I want to be careful with the tone here, because this is the point in the story where a certain kind of coverage takes over. The line about living inside a black hole travelled around the world in about 4 days in the spring of 2025. It travelled without the sample size. It travelled without the significance figure. It travelled without the second explanation, and it travelled without the fact that the person who made the measurement prefers that second explanation. The claim travels, the correction does not. We are going to see that pattern again shortly, in a much more emotionally loaded setting. But there is one more piece of cosmology to deal with first, and it is the one where the telescope was brought in specifically to settle an argument, and instead ended up on both sides of it. Part 10. 2 numbers that will not meet. The universe is expanding, and there is a number that says how fast. It is written as a rate per unit of distance, because that is how expansion works. The further away something is, the faster it recedes, not because it is moving through space particularly quickly, but because there is more space between us and it, and all of that space is stretching at once. The number tells you how much faster a galaxy recedes for every additional chunk of distance you add. The chunk conventionally used is the megaparsec, about 3.25 million light-years. There are 2 ways to measure it, and they have been giving different answers for over a decade. The first way looks at the oldest light in existence, the glow left over from when the universe first became transparent, about 380,000 years in. That light carries a pattern of faint ripples, and the sizes of those ripples are set by physics we understand well. Measure the ripples, feed them through the standard model of cosmology, and the expansion rate comes out at 67.4, give or take half a point. The second way starts here and works outward. You find something in a nearby galaxy whose true brightness you know, a particular kind of pulsating star, or the sharp maximum brightness that low-mass stars reach at the moment helium ignites in their cores, and you compare its true brightness with how bright it looks, which gives you the distance. Then you use that galaxy to calibrate something brighter that you can see further away, usually a certain class of exploding star. Rung by rung you climb out. It is called the distance ladder, and it has been built and rebuilt for a century. That method gives 73.18, give or take about 9/10, 67.4 and 73.2. They do not overlap. They do not come close to overlapping. The gap, as the team behind the second number computes it, is 5.8 sigma, well past the threshold at which physics stops calling something a fluctuation. That gap has a name. It is called the Hubble tension, and it is the largest unresolved problem in observational cosmology. It corresponds, if you want it in intuitive terms, to a disagreement of roughly 1 billion years about the age of the universe. So when a new telescope launched with better resolution than anything before it, the obvious thing to do was point it at the rungs of the ladder and check the work. 2 major teams did exactly that, and they got different answers. The first team, the one behind the 73, used the new telescope to reobserve their calibrating stars and found that their result held. 73.18 from a combination of methods across 55 exploding stars. 73.49 from the new telescope's data alone in the cleanest galaxies. The tension, from where they stand is real and getting harder to dismiss. The second team used the same telescope on overlapping targets with 3 independent calibration methods and got 69.85 from one method, 67.96 from another, and 72.05 from a third. Combined, 69.96, 69.96, which is close enough to the 67.4 from the oldest light that this team argues there may be no tension at all, that the whole thing is a problem in the distance ladder rather than a problem in physics. Same telescope, same sky, 73.2 against 70. Both teams are excellent, both are careful, both have spent decades on this. And here is the detail that I think is the most telling in the whole affair. Within that second team's own results, the 3 methods disagree with each other. 68 from one, 72 from another. That is a spread larger than their quoted statistical errors using the same data from the same group in the same paper, which means there is something systematic hiding in at least one of those methods that nobody has yet identified. The field has noticed. There is a paper whose title is simply a question: Hubble tension or distance ladder crisis. That question mark is the honest state of affairs in 2026. So the telescope did not confirm the tension, and it did not kill it. It split the community. And into that, in 2024, came something completely new, a way of measuring the expansion rate that does not use the ladder at all. There is a galaxy cluster with a catalogue name I will spare you. Behind it, much further away, a star exploded, and because the cluster's mass bends the space around it, the light from that explosion took 3 different routes to get here. Not 3 copies of an image, 3 routes, each one a different length, which means the same explosion arrived at our telescopes 3 separate times. The first arrival came in, then 116.6 days later the second, and then 48.6 days after that the third. Same star, same explosion. 3 sunsets, weeks apart, from one event that happened when the universe was less than half its current age. And if you know the time delays, and you can build a model of exactly how the cluster's mass is arranged, you can work backwards to the expansion rate, because the delays depend on the geometry of the whole path, and the geometry depends on how much the universe has stretched along the way. Here is how they did it, and this is the part I want you to sit with. They blinded themselves. The analysis was carried out with the answer deliberately hidden from the people doing it. 7 separate models of the cluster's mass were built independently. The time delays were measured without anyone being able to see what expansion rate they implied. The rules for what could and could not be changed after the answer appeared were written down in advance and agreed to so that nobody could quietly adjust a parameter after seeing a number they did not like. And then, at an agreed moment, in front of the team, the analysis was unblinded. The number came up: 71.8 plus 9.2 minus 8.1. Then they did something clever. The exploding star in question is a standard candle, a class of explosion whose true brightness is known, which means you can check each of the 7 cluster models against how much it magnified the supernova and throw out the ones that get the brightness wrong. Doing that tightens the answer to 75.7 plus 8.1 minus 5.5. As the paper puts it, people had theorized for a long time that a standard candle was the way through this, and nobody had been able to do it until now. It is the first precision measurement of the expansion rate from a multiply-image supernova of this type, and only the second from any multiply-image supernova at all. Look at those error bars, though, plus or minus 8, which means this beautiful, careful, blinded, independent measurement is comfortably consistent with 73 and, at a stretch, with 67. It agrees with everybody. It does not settle anything. What it does is demonstrate a method that could, with more systems and tighter delays, eventually settle it. A program is already running to double the precision on this one. I find this stretch of the story oddly comforting after everything else, because here is a field that knows exactly how easy it is to fool itself and has built elaborate machinery specifically to make fooling itself harder. Blinding protocols, independent models, rules agreed in advance, which makes it all the more instructive to look at what happens when a result arrives without that machinery and gets believed by the entire world in about 48 hours. Part 11. The molecule that was only made by life. There is a planet about 124 light-years away, in the constellation Leo, going around a small, cool red star. It is roughly 2.5 times the width of Earth and about 8.5 times its mass, which puts it in a size class we have no example of at home. Bigger than a rocky world, smaller than Neptune. The category is called sub-Neptune, and here is the thing about it. Sub-Neptunes appear to be the single most common kind of planet in the galaxy. The most common planet there is, and there is not one in our solar system, which means every structural model anybody has for them is untested against a nearby example. This one orbits inside its star's habitable zone, the band where liquid water could, in principle, exist on a surface. It transits, meaning it passes directly between us and its star once every 33 days, and during that pass a very small amount of starlight filters through the edge of its atmosphere on the way to us, and comes out the other side carrying the chemical signature of whatever it passed through. That is the entire technique. You're reading an atmosphere by the shadow it casts. The signal is a few hundred parts per million at best. You're looking for a change of a fraction of a percent in the brightness of a star, at particular wavelengths, during a few hours once a month. In September of 2023, a team from Cambridge published the first result. Using 2 of the near-infrared instruments, they found methane and carbon dioxide. That part is solid, and I want to give it its due before anything else happens, because it has been rather buried by what came next. Detecting carbon-bearing molecules in the atmosphere of a temperate habitable zone planet of an entirely alien class is a genuine first. It is a real achievement, it is held up, and nobody disputes it. They also noted an absence. Ammonia was in short supply, and argued that the combination pointed toward what they call a Hycean world, a planet with a hydrogen-rich atmosphere sitting on top of a global liquid water ocean. It is an appealing picture, and it is their own coinage, from a paper a couple of years earlier, and buried in that same paper was one more thing, flagged carefully below the threshold of significance, described in the text as tentative. There might, they wrote, be a hint of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is made by life. Specifically, it is made by marine plankton, in enormous quantities, and it is a large part of what the sea smells like when you stand near it. As of 2023, no one knew of any non-biological process that produced meaningful amounts of it. You can see where this is going. On the 17th of April 2025, the same group published again, this time using the mid-infrared instrument, a different detector, at longer wavelengths, looking at a completely different part of the spectrum, and they reported that dimethyl sulfide, or a close chemical relative called dimethyl disulfide, could explain what they were seeing at a significance of about 3 sigma. 3 sigma is roughly a 1 in 370 chance of arising from noise, 99.7%. The team said explicitly in the paper that this was below the 5 sigma standard physics requires. The university's press release was titled, "Strongest Hints Yet of Biological Activity Outside the Solar System." I do not need to describe what the next week was like. You were probably there. Now let me tell you what happened over the following year, because almost none of it reached the same audience. The first thing to notice is buried in the claim itself. The analysis could not distinguish dimethyl sulfide from dimethyl disulfide. The 2 molecules were degenerate. The data supported either, with no way to choose, and the abundance required was extraordinary, more than 10 parts per million against sub-parts per billion in Earth's atmosphere. Thousands of times more of this molecule than our own ocean-covered, plankton-saturated planet manages. On Earth, dimethyl sulfide is destroyed by chemical reactions with a lifetime of about a day, so those levels would demand a source of colossal, continuous output. Then the reanalyses began. One researcher applied the simplest possible test to the mid-infrared data. He asked whether the spectrum was distinguishable from a flat line. A straight horizontal line, no features at all. It was not. Statistically, that spectrum is consistent with nothing happening, and if there is no feature, there is nothing for any molecule to explain. A second group from Chicago ran a joint analysis across all 3 instruments simultaneously, the 2 near-infrared datasets and the mid-infrared one together, rather than separately. Their conclusion was in their title, Insufficient Evidence. They also showed that the answer depends on which data reduction pipeline you use, which is not supposed to happen. A third result, and this one is the most quietly devastating, came from a group at Arizona State. The method used to make the original claim is called Bayesian model comparison. You supply a list of candidate molecules, you fit each one, and the method tells you which fits best. And what they showed is that if you extend the list, other molecules do better. In particular, propine, a perfectly ordinary hydrocarbon, no biology anywhere near it, comes out with higher evidence than dimethyl sulfide. Which means dimethyl sulfide was never the best explanation of the data. It was the best explanation among the ones that had been tried. I want to stop on that, because it is the single most important methodological point in this entire episode, and it generalizes far beyond one planet. A model comparison always returns a winner. It has to. It ranks the hypotheses you gave it. It has no way of telling you that the true answer was not on the list, because it has never heard of the true answer. The confidence number that comes out the end is a statement about the contest you organized, not about the universe. A 4-3 analysis of the near-infrared data reported that for most of the species involved, you can only set upper limits at the 2 sigma level, not detections, limits. And then there is the detail that I think about more than any of the others. The mid-infrared data have to be grouped before they are fitted. You bin the measurements together, because individually they are too noisy to work with, and you have to choose how wide the bins are. Somebody went and checked what happens under a different, equally reasonable binning scheme. 87.5% of the time the signal does not reproduce. The data did not change. Not one photon changed. The choice about how to group the numbers before looking at them changed the answer. We have been here before. In part 3, at the very start of this, there was a galaxy that appeared to sit at a redshift of 16, and the entire claim came down to a bump in a graph. One filter reading higher than its neighbours. That was a bump in the wrong filter. This is a bump in the wrong binning. Different instrument, different wavelength, different continent, different decade of the mission. Same shape of failure. And the ground has moved under the biology too. Dimethyl sulfide has since been found on a comet, detected in data from a European spacecraft that flew alongside one for 2 years. It has been found in a cold cloud of gas near the centre of our own galaxy, where there is no chemistry more complicated than dust and starlight. And laboratory and modelling work has demonstrated a purely chemical route to making it. Take methane and hydrogen sulfide, add ultraviolet light, break them apart, let the fragments find each other. No life anywhere in the reaction. So the premise the whole story rested on, this molecule is made only by living things, is no longer true. It was a reasonable rule of thumb about Earth in 2023. It is not a rule about the universe. Where does it stand now? In the last stretch, a team led from the Jet Propulsion Laboratory went and got 4 more transits of the planet, more months of scheduling, on a world that passes in front of its star only every 33 days, combined them with everything that already existed, and then handed the whole dataset to 3 independent groups, including the original team, and asked each of them to interpret it across a broad range of possible atmospheric compositions rather than one favoured model. The result? A water-rich atmosphere, methane confirmed, carbon dioxide confirmed, no conclusive evidence of dimethyl sulfide. There is now a peer-reviewed paper whose title states the position plainly, that the planet does not meet the standards of evidence for life, and a 2026 review that asks in one of its own section headings whether this molecule still works as a biosignature at all. Its table of results across all the competing analyses shows this compound listed over and over as an upper limit rather than a measurement. And I want to say the honest thing about how that week in April felt, because I do not think anybody should be embarrassed about it. An enormous number of people believed, on entirely reasonable authority, in a properly peer-reviewed result from a serious group at a serious institution, that we had found the first trace of life beyond this solar system. That belief was not foolish. It was the correct response to the information available, and what took it away was not a better telescope, and not a closer look at the planet, and not some new fact about biology. It was a decision about how to group a column of numbers before drawing a curve through them. The planet never changed. The planet is exactly what it was in April of 2025, going around its little red star once every 33 days, with methane and carbon dioxide in its air and a great deal of water somewhere in its structure. We were never actually asking it the question properly, and the story does not end there, because when the same telescope turned to the small rocky worlds, the ones that were supposed to be the real prize, it did not find life, or the absence of life. It found something harder to work with than either. Part 12. The Air That Isn't There. Before this telescope launched, if you had asked anybody where the first genuinely Earth-like atmosphere would be found, most of them would have given you the same answer. 40 light-years away there is an ultra-cool red dwarf star with 7 Earth-sized rocky planets going around it. 3 or 4 of them in or near the habitable zone. It is the best stocked system anybody has found. It has been the flagship target for a decade. Everything about it was set up to be the place where the answer came from. The first planet examined was the innermost. The measurement is elegant. You watch the system as the planet passes behind its star, and you subtract. What disappears when the planet goes behind is the planet's own heat, and from that you can work out how hot its dayside is. The answer came back at about 500 Kelvin, roughly 230 degrees Celsius, and crucially, consistent with no heat being carried around to the night side at all. That is the tell. An atmosphere moves heat. Winds carry warmth from the day side to the night side, and the temperature difference gets smaller. If the day side is as hot as it would be with nothing at all in the way, and the night side gets nothing, then there is no atmosphere thick enough to matter. A follow-up analysis at a second wavelength concluded the planet is probably a bare rock with a mineral surface. Thick carbon dioxide atmospheres, up to and including a full Venus-like 92 bars, were ruled out. The second planet gave the same kind of answer. Its eclipse depth was measured at 421 parts per million, plus or minus 94, which is consistent with bare rock, or at most a thin, low carbon dioxide atmosphere. Venus-like scenarios disfavoured, which means that planet has far less carbon dioxide than Venus does. It either formed without much, or something took it away, and there is a good candidate for something taking it away. Red dwarfs are violent when they are young. For hundreds of millions of years, sometimes billions, they flare, and they pour out high-energy ultraviolet radiation far out of proportion to their size. A small planet on a tight orbit around one of those sites in that weather for its entire formative history, and an atmosphere is not a permanent fixture. It can be stripped. This has a name now. People call it the M-dwarf atmosphere problem, and it is a properly cruel piece of cosmic design if you think about it. Small cool stars are by far the most common kind of star in the galaxy. Their planets are the easiest to study, because the star is small so the planet blocks a bigger fraction of it, and the orbits are short so you get transits often. Every advantage points at red dwarfs, and red dwarfs may be the stars least likely to let a planet keep its air. But that is only the first problem. The second problem is worse, because it is not about the universe at all. Consider another planet, a rocky super-Earth about 26 light-years away, around another red dwarf. The spectrum came back showing a signal consistent with water vapour, except the team could not determine whether the water is in the planet's atmosphere or on the star. Cool stars have water vapour in their outer layers, and their surfaces are blotchy. Cooler spots, hotter bright regions, and a planet transiting across a blotchy star imprints the blotches on your measurement. If the planet happens to cross a cool spot, the light you compare against is not the light you assumed. The team's own summary of the result was that it is either a planet with a hot atmosphere of water or a star with cool star spots, and they could not tell you which. That is the situation for essentially every small planet around a small star. The planetary signal is a few tens of parts per million. The star's own patchiness can produce hundreds. The star is louder than the planet, which brings us to the one everybody actually cares about in that 7-planet system. The 4th planet out, the one squarely in the habitable zone, the single most promising rocky world we know of. 2 companion papers landed in the autumn of 2025, based on 4 transits taken with the near-infrared spectrograph. All 4 transits showed evidence of contamination from the star. The teams had to model the star as carefully as the planet just to see anything. What they could rule out: a puffy, cloudy, hydrogen-dominated atmosphere at better than 3 sigma. That kind of envelope is not there. What they could not rule out: essentially anything else. A heavy, nitrogen-rich, Earth-like atmosphere is fully consistent with the data. So is a Titan-like one. So is a thin carbon dioxide one. So is nothing at all. Both headline versions that ran in 2025 were wrong. It does not have an atmosphere, and it may have an atmosphere, are both overstatements of a result that says, we have excluded one option out of many, and we need a great deal more time on this. And then, in July of 2026, 1 month ago, the other direction. A different rocky planet, a temperate super-Earth about 48 light-years out, long regarded as the best remaining candidate after this system disappointed, produced what has been reported as the strongest evidence yet that a rocky world in a habitable zone has held onto its atmosphere. If that holds, It is the direct answer to the M-dwarf problem, proof that at least some small planets around small stars keep their air. I want to be careful with it precisely because of everything we have just been through. It is new, it has not been independently replicated, it is the strongest evidence so far, which is a different statement from settled. So let me finish this stretch with the control group, because it is the part that makes all of the above meaningful rather than merely discouraging. There is a bloated gas giant about 700 light-years away, roughly Saturn's mass inflated to Jupiter's width, whipping around its star every 4 days at 900 degrees Celsius. In July of 2022, the spectrograph found carbon dioxide in its atmosphere, the first clear, unambiguous detection of carbon dioxide anywhere outside our solar system, not at 3 sigma, at around 26. A signal so far above the noise that arguing about it would be a category error. The same campaign found sulfur dioxide, which was more interesting still, because that molecule cannot exist there in chemical equilibrium. It has to be manufactured by ultraviolet light from the star breaking apart other molecules and letting the pieces recombine. That was the first evidence of photochemistry, light-driven chemistry, the same broad process that builds Earth's ozone layer, in the atmosphere of another world. And then, in 2024, a different instrument, working at different wavelengths in a separate paper, found it again. That is the whole difference. That is the entire lesson of tonight in one comparison. 2 instruments, 2 wavelength regimes, 2 analyses, same answer, and nobody has argued about that result since. The same is true of the strangest weather report in the catalogue. There is a hot Jupiter about 1,300 light-years away, so puffed up that it has 7 times Jupiter's volume at half its mass, which makes its atmosphere unusually easy to see through. Over a 10-hour transit, more than 1,275 separate brightness measurements were taken across the mid-infrared, and they showed an absorption feature at 8.6 microns that the usual cloud materials cannot produce. The clouds on that planet are made of quartz, actual crystalline silica, in crystals about 10 nanometers across, a millionth of a centimeter, roughly a 10,000th the width of a hair, suspended in the air. And the way they form inverts everything your instincts tell you about quartz. On Earth, quartz is what you get at the end, weathered, ground down, washed into sand. Up there, at 1,000 degrees and 1,000th of Earth's surface pressure, the crystals condense directly out of the gas, straight from vapor to solid, skipping the liquid stage altogether, exactly the way a snowflake forms out of humid air. The quartz is not the debris, it is the seed, and on a tidally locked planet with winds of thousands of miles per hour, those crystals are swept from the burning day side around toward the edge, vaporized and condensed again, endlessly. That has since been found on a second planet, so it is a class of world, not a curiosity. I want you to hold both halves of this together, because the contrast is the point. The results that survived were the ones where a second instrument at a different wavelength went and looked and saw the same thing. The results that did not survive were the ones where everything depended on how one dataset was handled. Which brings us to the last of them, and this one is the hardest, because it was not a tentative hint that got oversold. It was a 4 sigma detection, in a completely different kind of light, of the most important object in the story. Part 13. The detection that undetected itself. To understand why this one mattered so much, you have to understand the problem it was supposed to solve. Almost every large galaxy has a supermassive black hole at its center. Ours does. The one next door does. And nobody knows where they came from. There are 2 candidate answers, and they have been arguing with each other for 20 years. The first is the modest one. Call them light seeds. The very first generation of stars formed out of pure hydrogen and helium, with no heavier elements to complicate matters, would have been large, tens to hundreds of times the mass of the Sun, and they would have died fast, and some of them would have left black holes behind. 10 solar masses, maybe 100. That is your starting point, somewhere around a few 100 million years in. The trouble is the arithmetic. To get from 100 solar masses to 10 million, you have to eat, continuously, at essentially the physical maximum rate without interruption, for the entire time available. And the physical maximum rate is real. Infalling matter heats up and radiates, and the radiation pushes outward on whatever is still trying to fall in. Feed too fast and you blow away your own supply. It is like trying to fill a bath while standing on the plug. The second answer is the dramatic one. call them heavy seeds, or by their proper name, direct collapse black holes. The idea is that a cloud of pristine gas, tens of thousands, maybe 100,000 solar masses of it, collapses in one piece, without fragmenting into stars at all, and goes straight to a black hole. You would begin at 10,000 or 100,000 solar masses instead of 100, and suddenly the timing is comfortable. But it requires very particular conditions. The gas has to be prevented from cooling efficiently, which normally means it has to be bathed in ultraviolet light from a nearby young galaxy at exactly the right intensity. And nobody has ever unambiguously seen it happen. So when, in 2023, a team announced that they had found one, it was a very large deal. The object sits behind a massive galaxy cluster which magnifies it. Combining the Space Telescope's infrared imaging with a long stare from an orbiting X-ray observatory, the team identified a heavily obscured, actively feeding black hole at a redshift of about 10, roughly 470 million years after the beginning, when the universe was at 3% of its present age. The numbers they published, a black hole of around 40 million solar masses in a galaxy whose entire population of stars weighed about the same, not 0.1%, which is the ratio you find nearby. Comparable. The black hole was as heavy as everything else in its galaxy combined. They called it the first overmassive black hole galaxy, and they described it as compelling evidence for heavy seeds from direct collapse. It went into every review, every talk, every documentary, including, I would guess, some you have watched. On the 26th of March, 2026, a different group published a reanalysis. They had something the original team did not, the complete X-ray dataset. 2.2 million seconds of observing time on that patch of sky, including 950,000 seconds that had never been published by anyone. Let me put 2.2 million seconds in front of you properly, because the number is doing something that the phrase X-ray observations completely hides. It is 25 days. 25 continuous days of an orbiting telescope staring at one small region of sky, and what it is doing during those 25 days is counting individual photons, one at a time, as they arrive, not thousands per second. Sometimes one, then a long wait, then another. You cannot see anything in an hour of that. You cannot see anything in a day. What you do is accumulate. You let the pile grow, and the whole logic of the measurement rests on one simple expectation. If there is a real source sitting at that position, the pile grows. Every extra hour adds photons at a steady rate, and the signal climbs out of the background, and the longer you stare, the more certain you become. So watch the pile. It does not grow. That is the finding, and it is quietly devastating. The apparent excess of hard X-rays at that position does not strengthen as more exposure accumulates, which is not how a real source behaves. There is more. The original detection was reported at 4.2 to 4.4 sigma. Across the full range of reasonable ways of reducing the complete dataset, the significance comes out between 2.3 and 2.9, and critically, the original higher figure turns out to depend on exactly how the X-ray image was aligned with the infrared one. Shift the alignment within its own uncertainty, and the detection moves. The reanalysis says, in the technical phrasing that these papers use when they are being polite, that it is not robustly reproducible, and then the mid-infrared. The Space Telescope has 9 imaging filters in that range, and a heavily obscured, ferociously feeding black hole should light up in them, because the dust doing the obscuring has to dump that swallowed energy somewhere, and it dumps it as heat. The object is undetected in all 9. Fitting obscured quasar templates to the tightest of those limits caps any hidden black hole at roughly a quarter of the luminosity originally claimed. Independent spectroscopy in 2026 found no signatures of an active nucleus in either the ultraviolet or the optical. The conclusion, in the paper's own words, is that the data paint a consistent picture of a low-mass, metal-poor, star-forming galaxy in the early universe, with no compelling evidence for a luminous, obscured black hole, regardless of its proposed formation channel. It is a bump in a graph. That is all it ever was. In part 3 it was a bump in the wrong filter, and a galaxy fell from 16 to 5. In the last part it was a bump that changed depending on how you grouped the numbers, and a biosignature evaporated. Here it is a bump in a count of X-ray photons that never grew, and the best observational evidence for how supermassive black holes are born goes with it. 3 claims, 3 different instruments, 3 different wavelengths, 3 different fields of research, 3 different decades of scientific tradition behind them. All 3 failed at the same step. Not one of them failed at the telescope. Now, I want to draw your attention to something about that reanalysis that has nothing to do with astrophysics. Look at who wrote it. Among the authors are two of the most prominent theorists working on precisely this question. People who have spent years building the case that early black holes are overmassive, that heavy seeds are necessary, that direct collapse is how it happened. One of them has been among the loudest advocates for exactly the interpretation this paper dismantles. Nobody made them do that. There is no prize for it. There is no headline in it. You did not see this on the news in March, and I would be surprised if you had heard of it before tonight. It is a negative result about somebody else's discovery, published by people whose own program it damages, using data they had to go and dig out because 950,000 seconds of it had never been written up. That is the least visible act in this entire story, and it is the one everything else depends on. Every fact I have told you tonight that you can trust because of behaviour like that. I should be careful, though, because this is a preprint marked as submitted, which means it may not have finished peer review. The honest phrasing is that a reanalysis using the full dataset finds the detection does not hold up. Not that it has been retracted. The correction is itself provisional, which is exactly as it should be. And the seed problem, of course, is now worse than before, because the other flagship candidate is not a candidate either, not quite. In July of 2025, a team at Yale published something extraordinary from a wide survey. 2 galaxies caught in a head-on collision, each one wearing a ring of shocked gas thrown outward by the impact, and the 2 rings side by side making the shape of a figure 8. They called it the Infinity Galaxy. The shape got the attention. What matters is what is sitting in the middle of it. There is an actively feeding supermassive black hole of about 1 million solar masses, and it is not at the centre of either galaxy. It is in the gas between them, and it is moving with that gas rather than with either nucleus. A black hole made the ordinary way should be at the centre of a galaxy, because that is where it formed, and that is where the dynamics keep it. A black hole sitting in shocked, compressed gas between 2 colliding galaxies, drifting along with that gas, is much more naturally explained as having formed right there, a direct collapse, possibly caught in the act, and the scientist who found it has been scrupulous about it. Asked directly, he has said they cannot claim definitively that this is a direct collapse black hole. New observations have strengthened the case and eliminated some alternatives, a black hole flung out of one of the nuclei, or one belonging to a third galaxy too faint to see, but the honest word remains candidate. There is also a wrinkle in it that cuts both ways. That collision is at a redshift of about 1, which is to say roughly 8 billion years ago, nowhere near cosmic dawn. If direct collapse can still happen that recently, in an ordinary galactic pileup, then it is not a special one-time process of the pristine early universe at all. And there is one more black hole worth 30 seconds, because it inverts the usual anomaly. There is an actively feeding black hole confirmed at a redshift of 8.6788, about 570 million years in. Its mass is roughly 9 million times the Sun, and the reason it is strange is not that it is too big. Compared with the billion solar mass monsters found at later epochs, it is small. It is strange because it is still bigger than any growth model can produce in that time. It is stuck in the middle, too heavy for a light seed, too light to be one of the giants, which suggests the problem is not with the extreme cases at all. The whole distribution is wrong, so we arrive at the end with the seed problem intact, the 2 best pieces of evidence for its most popular solution either withdrawn or explicitly unclaimed, and a brand new class of object proposed 5 days ago that would, if it is real, be a 100,000 solar mass black hole at cosmic dawn by an entirely different route, which leaves one question, the one I promised you at the beginning, and it is time to answer it plainly. Part 14. What the grain of sand was holding. The disturbing thing is not any of the objects. I have spent this evening showing you objects, and some of them are genuinely difficult. A galaxy full of oxygen before there should have been oxygen, hundreds of red points with no agreed classification, a dwarf galaxy that fell silent 700 million years in. But none of those is the answer to the question I asked you at the start, and I have been holding the answer back, so here it is. The disturbing thing is the pattern of the failures. 4 times now, a headline result from the most successful scientific instrument ever built has been undone. Not by better data, not by a better telescope. In every single case, the original photons were fine, the detector was fine, the hardware performed exactly as designed. What failed, every time, was the last step. the step where somebody has to decide what the numbers mean. A galaxy at redshift 16 was a bump in the wrong filter. 6 impossibly heavy galaxies were a modelling assumption about where the light was coming from. A biosignature 124 light-years away was a choice about how to group data before fitting it. And the best evidence anyone had for how supermassive black holes are born was an X-ray excess that depended on how one image had been aligned with another, and that never grew. That is not a story about scientists being careless. Every one of those claims was made honestly, published in a serious venue, and checked by referees. It is a story about what happens at the very edge of what an instrument can do, where the signal you're chasing is small enough that the way you handle it becomes part of the answer. Out there, the boundary between a discovery and the shape of your own assumptions is thinner than anybody was prepared for, and you cannot see which side of it you're on from the inside. That is the disturbing part. Not that we were wrong, that there is a region, at the frontier of every instrument ever built and every instrument that will ever be built, where being wrong and being right look identical from where you are standing, and now subtract all of it. Take away every claim that failed, throw out the galaxy at 16, throw out the impossible masses, throw out the biosignature and the direct collapse black hole and the rotating universe. Delete every headline of the last 4 years that did not survive contact with somebody checking. Look at what is left. There is a galaxy at 14.44, confirmed by a sharp break and 5 separate emission lines, 280 million years after the beginning of everything. There is another one whose redshift was measured to 4 decimal places by 2 different observatories using 2 different techniques, and it contains roughly 10 times more heavy elements than it should, which means an entire generation of stars had already been born, burned and died 290 million years in. There is a black hole 9 million times the mass of the Sun, feeding at 570 million years that no growth model can account for. There is a galaxy that made everything it would ever make in a window shorter than the age of the Atlantic, and then went quiet at 700 million years, with none of the mechanisms that are supposed to be able to quiet a galaxy yet in existence. And there are hundreds of small red objects that were invisible to every telescope that came before, that are not in any category we have, and for which serious people published 2 mutually incompatible explanations within 7 days of each other this month. Every one of those survived. None of them can be explained away as a bump. The universe did not wait. I have said that twice tonight, and this is the last time. It did not wait to make the elements. It did not wait to build the galaxies. It did not wait to grow the black holes. And in at least one case, it did not wait to stop. Everything we built assumed a schedule, and there was never a schedule. There was only a universe getting on with it, in the dark with nobody watching, 400 million years before it had finished making the transparent space for the light to travel through. And I keep coming back to the sand, that first image from the 11th of July 2022, 12.5 hours, a patch of sky the size of a grain of sand held out at arm's length by somebody standing on the ground. When we started, that was a charming way of saying a very small piece of sky. It was a scale image, a bit of poetry from a press office. It is not that anymore. We have spent tonight going through what turned up inside that grain of sand and the handful of others like it. Records and corrections and objects with no name, an entire population nobody can classify, a galaxy holding its breath, a black hole that outweighs its own home. That is what one grain of sand held. Now hold your arm out again and look past your fingers at the rest of it, at all the sky that is not that grain. That is the thought I cannot put down. There is one thing I want to leave you with, though, because I do not want to leave you in the wrong place. You will hear it said that all of this means the Big Bang has been disproved, or that cosmology has collapsed, and I want to be clear that this is not what happened, and the reason is quite neat. Every single anomaly we have discussed tonight is measured using redshift, and redshift only means distance and look-back time inside an expanding universe. Take away the expanding universe, and none of these objects has a distance, or an age, or an anomaly. The claims depend entirely on the framework they are supposed to be overturning. What is genuinely under pressure is how fast structure assembles inside that universe. The universe itself is fine, and the corrections, the ones nobody covered, the reanalyses, the flatline tests, the 25 days of X-ray photons that stubbornly refused to pile up, those arrived within 1 to 3 years, in the open, sometimes written by the same people who made the original claims, and in at least one case by the people with the most to lose from them, That is not a system failing. That is the fastest error-correcting machine our species has ever built, running at full speed under more data than it has ever had to handle. So this telescope looked further into the universe than anything before it, and what it found is disturbing. Not because the universe turned out to be broken, but because it turned out that at the far edge of seeing, the hardest thing to measure is the distance between what is there and what we expect. Everything that survived that measurement says the universe was busier, faster, and further along than we thought at every point we have managed to look. And we have looked at a grain of sand.